in working with linear functions, we need to be able to work with context and model scenarios with linear functions, which means context, word problems, yep, we're going to have to do it. And these models, I think it's very helpful to keep that model variation that we talked about in the last video of, you know, the rate of change times x, or times the input, times or plus your initial value. That's super helpful when constructing a model, like in this first example. Okay, so we're talking about speeding tickets. Okay, don't get a speeding ticket, they're expensive. Is kind of the moral of this problem. But so we state, says, okay, it's $125 flat fee if you're speeding, and then for every mile an hour over the speed limit that you go, it's an additional $15. And so if we look at constructing a model, okay, so I'm just going to write this out, part A. So I need to say f of x is equal to mx plus b. Now, technically here, yep, I understand what you're saying, but x and f of x here mean something in context. So whenever you are constructing a model without any guidance, on some instances, it says like, let x be this, let y be this, or f of x be that. That's fine, use those variables, but otherwise, if you are introducing notation, you need to define it. So I'm going to come off to the side here and say x is something and y is something. Okay, so it says write a linear function to model the cost of a speeding ticket based on the mile per hour over the speed limit. Okay, so when I see this language as an expert, okay, to model the cost of a speeding ticket, okay, that's one variable based on the miles per hour over the speed limit. Okay, so this language based on is super critical because what that's telling me is that the cost of the speeding ticket is computed only if I know the mile per hour over the speed limit that I'm going. So this is my input. This is my x. Okay, I have to put this into the model in order to be able to calculate the cost of a speeding ticket. So this is what I get as my output, my y value. Okay, so here I would define x as the miles per hour over the speed limit. Okay, so I have to put that in, and then y, which is the same as the function value, is the cost of the speeding ticket. Okay, so then now that really helps, because then I can think about this as, my rate of change times x plus my initial value. Okay, for f of x. Okay, so f of x is just going to equal f of x. We're going to have to leave it in general, but then what is, maybe let's start with the initial. How much is the initial charge? How much is the initial cost? $125, right? So plus 125. I'm charged $125 no matter what if I speed. Okay. And then how much, so x is the miles per hour speed limit. So how quickly is the cost changing based on how much you speed? That's the 15. Okay. So 15x. All right. So 15, and sometimes writing out the units helps. So like m, if you were to write out the units of change in y over change in x, okay, this would be cost is in dollars per miles per hour over. And so then if you look at the 15, okay, so it's $15, right? Dollars per mile per hour over, okay? So sometimes just writing out the units in these contexts helps you determine the model. But regardless, we have our model in part A. Part B, it says evaluate your function for 10 miles over the speed limit and interpret the meaning of it in context. So this is maybe a quicker part, but this is saying now if you are 10 miles an hour over, so you're inputting 10, okay? 15 times 10 plus 125, okay? This gives you 150 plus 100, 125 is $275. Ooh, that's a big bill. Okay, so then this means in context, if you are speeding by 10 miles an hour, your ticket will be $275. Okay, there we go. Part C, it says, what is the value of the vertical intercept? So vertical intercept is our initial value. So C, this is $125. Okay, and what meaning, if any, does it have in this context? Well, that just means it is the base fee if you are caught speeding. Okay, and you can expand on this, like you can also say, if you pay that amount in addition to $15 for every mile an hour you're over, et cetera, et cetera. So there we go. The hardest part of this entire thing, part A, getting that model, getting that function written out. And again, if it's easier for you to look at this in a table form, you could say, okay, well, what's our input and what's our output? Well, if we put in 0, if you are 0 miles an hour over, you're $125. Your ticket fee is $125. And then if you're 1 mile and over, that's $140. 2 miles an hour would be $155. And you could construct a table to help you build the model too. That's always an option. All right. Next one. Okay, so it says data below represent age and systolic blood pressure from a sample of 12 randomly selected healthy adults. Okay, so we have adults with age and their systolic blood pressure given. Okay, so this says that suppose X represents the age of an adult. Okay, so now here, this is telling you your variable. So age is X and Y is their systolic. Okay. So it says, use the points to construct a linear model where y is a function of x, okay? And so, okay, well, we need to maybe just build the model. So f of x is equal to mx plus b. I need to find m, right? So m is equal to, let's see, so it'll be 130 minus 118 over 51 minus 21. Okay, so this is 12 over 30, right? And then this can reduce to 2 over 5. Okay, so we have our slope, and then I'm going to take a different way to find b. Okay, as you know, I'm a big fan of the slope-intercept form. Okay, y minus y1 is equal to m x minus x1. Okay, you can totally do this to find out what b is. So we know that a point here is 118 and then 21, and we know the slope is 2/5. Okay, so then I'm just going to solve for y. I'm going to put y on one side alone. I'm going to have 2/5 x minus, distribute the 2/5 to both of those, so it would be 42/5 plus 118. And so then if you simplify this, 2/5 x, you have to get common denominators and all that jazz. You end up with plus 548 over 5. Okay, and so this is actually our model. I'm just going to change the y to f of x. And when I do this algebra, the intercept pops out, that initial value pops out. Okay. Okay, now for time purposes, I'm just going to kind of talk through B and C, and then I'll leave you to calculate D. I want to talk about E for sure, though. So what meaning does the slope have? Okay, so the slope would mean 2/5. Okay, that is the rise over the run. Okay, so if we look at this up here would be the systolic blood pressure. And then down here, this is the age in years. So we would say if we increase the age in years by 1 unit, because again, we could view this as 1, okay? If we increase age in years by 1 unit, systolic blood pressure would increase by 2/5, okay? Alternatively, 2/5 millimeters mercury. Alternatively, we could say if we increase age by 5 years, we would expect that the systolic blood pressure would increase by 2 millimeters mercury. Okay, so that's two different ways of saying the same thing for the slope. What does the vertical intercept have to do with anything? So here, what does it mean? So if we were 0 years old, like just born, we would expect to have a systolic blood pressure of roughly 110. Okay, it's 109.6. Okay, so that's what this would mean. If we had an age of 0, the systolic blood pressure would be 109.6. Okay, part D, I'll let you estimate that. It's just substituting in. Part E is maybe a little bit more interesting because it's a little bit of a statistical tool. Okay, but what we're going to do is to make a scatter plot. You may already know how to make a scatter plot of the data, but I want to show you how to do it using Desmos. Okay, so I'm going to go to Desmos. I have it pulled up, desmos.com/calculator, and I'm going to insert the values from the table. Okay, so I'm going to pause the video, type it out, and then resume the video when everything's typed out. All right, so I have the data typed out, and again, to do a table, you just do plus and then do a table. Okay, but now to see the data, right, I have to make sure my window's in the right viewing range. So there's the data, and again, all these values are in the hundreds, so make sure that your vertical axis goes up to the hundreds, and you can see my horizontal axis is there too. So now it said, investigate the data using a scatter plot. So at least the scatter plot, it seems to say that as you get older, time in years, or age in years, right? That's the horizontal axis. Your systolic blood pressure, which is your vertical axis, increases, right? All right. And then a least squares regression model, it's effectively a trend line, okay? Trend line. And to get that in Desmos, what you're going to do is you're saying that you want to predict the value of y1. So do y_1, and then there's a tilde. So to get the tilde, it is shift, and then it's in the upper left corner of your keyboard, okay, right below escape. And then you do y tilde that, and then a x subscript 1 plus b. Okay, and the idea is that you can't use m, you have to use a and b here, but a functions the same as m. So you have to use x1 and y1 so that it knows to use your data table that you've already defined. But then here you get your equation of a line. So you could say the regression model would be y is equal to use this value of a, and then x plus, and then that value of b. All right. So formally, we'll just capture those in the exercise. And here was what we saw in Desmos. So writing that as y is equal to m 0.51 x plus b, that 104.17. And that's it. So the instructions here are rather vague, just kind of investigate and use a least squares regression model. And again, you can do all that in Desmos.